Okay. Well, then, yeah, let's start. Well, it is my pleasure to welcome Nikolay Britavskiy here. Nikolay graduated from physics with a master in Odessa National University in Ukraine. And then he moved to Athens, to the National Observatory of Athens, to do his PhD based on dusty massive stars in the local group. And then he went into the Instituto Astrofísico de Canarias to do his first postdoctoral fellowship, which was also concerned about the properties and the evolution of massive stars. And currently he is at the University of Liege, also investigating the nature of fast O-1p rotators. So,
yes, thank you very much for inviting. I just want to
you started screen sharing. Yes. All right.
Yeah,
I think it's.
Yeah, but why I don't see
your screen sharing. Maybe if you do the play from start, it will. Full screen. Yeah, maybe just try to make it full screen and let's see if. Now I see it in my.
Yes.
Yeah. Okay.
Yeah, now it's showing.
Yeah.
No,
Yes. Okay. Now we're good.
Okay.
Yeah. So the floor is yours.
Okay. Thank you very much for introduction. Thank you very much for giving this opportunity to share results, which results of the work which I was doing actually the last 3-4 years when I started in physical science, and now I'm kind of continue it in Liege, and now I'm willing to continue more. And mainly, my interest was to investigate why we have non-uniform distribution of the rotational velocities in the early type stars. And about this, I will speak today, actually. So let's start actually from the ancient times, when people first time noticed that if we will plot the rotational velocity of, in this case, O-type stars, like in a given volume, that we will see that we have kind of non-uniform distribution. We have like one peak in the slow rotating domain and some fast rotating tail. And now, here I'm citing this paper from 1977, where actually people define it empirically who is slow and who is fast rotator. So like each star with a rotational velocity is with sinus I less than 200 km per second is a slow rotating, and like people agreed that okay, everything what is more than 200 km per second we define as a fast rotator.
So sorry, is there an observational bias? Like, do you see all of them the same way, or are you less like?
Very nice question. I will answer in the next half an hour. There is no bias. I will answer to you. We will, because okay, here this distribution among like giants to dwarfs, Galactic O and the galaxy, and only late O-type star. The next paper, also quite early one, we can see such distribution among all early type stars, like from O to A, and we will see, that they have all this kind of strange distribution, and even if we will go a bit beyond our galaxy and look on the Magellanic clouds, we will see that the same thing is regarding some even clusters in the Magellanic clouds. So this distribution of vsini we see everywhere, and all this very early paper, okay, it's not very early anymore, but all this paper will discuss why we see it. Why it's happening like this. What is the actual reason of such rotational distribution? And with this question, I also, arrived like several years ago when we I mean, start to analyze all B-type stars within the ECHO project. It's like a multi-epoch survey of all B-type stars, which actually carry out in the AC, led by Sergio Sanagid. So that's our observational sample. Again, in the galaxy. In the given volume, like the distances and the magnitudes are, I can show you later, answering to your question, that more or less we are uniform in terms of, volume around us, which we, the stars which we have analyzed. And that's kind of main outline, mainly to understand what's going on. What is stars?
Looking at this, it seems very artificial to put the division in 200 because there is a peak and there is a long tail. So I would, by eye, it seems like 150 would be kind of there.
I agree with you. That's artificial, but again, it's kind of historical reason. 100 kilometers per second.
So is it motivated by physics, stellar physics, or just kind of a legacy?
It's not motivated by stellar physics, but now, if we will move to the theoretical predictions, which is Selma, she also used 200 kilometers per second as a threshold.
Yeah, but see, here it looks more separate.
Okay, of course, it's more separate because maybe it's very good because it's very, selected by luminosity of the stars, and it is artificial. And plus, it doesn't matter. Plus minus 50 kilometers per second is the same, but. The main question why we have such long tail and what is the actual nature of these objects. And okay, according to the reference definition, several hypotheses were proposed that it was initially spin up from no reason up to such high velocity, or it actually nowadays, and my recent work actually have some indirect hints that maybe all or not all, but majority of the stars are post-interacting binaries, which by different channels reached by this rotation. So okay, we have predictions, we have this empirical distribution, and now we were studied in detail. And to do this, we have in total like 54 fast-rotators in our galaxy, and then we did everything what we could with all tools which we have in our hands, like from multi-epoch analysis, proper motion analysis, investigate all TESS light curves, also to see, since later I will show you how TESS look perfect at some point in terms of the size of the pixel. So we're also looking for some visual component, which you can see around it. And now I will just show you some results, what we have found out. So first, that's kind of an example of different spectroscopic.
So can you tell us what type of stars they are? Does it depend?
All late O-type stars.
So late, okay.
From and mainly like luminosity class from 5 to 3. So not super giants, not super giants, but.
Is there a mass range for these stars?
We were aiming to select like more than 8 and less than 20 solar masses initially, but according to the again. So I'm here like an example for 8 of our stars, and like to see like we have some clear spectroscopic data in binary, 2 components binary, 1 component spectroscopic binary, when just one. We see just 1 component and the line is shifting, and of course some difficult cases where we are kind of not sure what's going on, because we also should keep in mind that line profiles of these stars are very broad, so very difficult to understand do they have some another component or not.
Excuse me.
Yeah.
Why is it that you have only relatively late O stars. You don't have earlier ones like 0.05 or 0.06. You have 0.07 there. The earliest.
No, personally, how the survey were built initially in terms of observations, but again, we don't see much fast rotators in the very.
But that is just because the numbers are low. I mean, they're like much less or very early stars, or it's because maybe something else that we don't know.
I think it's our selection of spectral type first, but
it's mostly then
yeah, mostly
the method you follow.
Yeah.
Okay.
Because also like evolutionary late O and early B are kind of in the same stage, while the early O is didn't detect much.
But maybe it's just because you have lower numbers, because they are more massive, so you have less numbers, and therefore the details will be much less.
I will show the HRD diagram later, where I placed with the temperature. Yeah, but it's a very nice point. It should be taken into account when we interpret the data. Okay. Here are just some examples that, since it's all-type stars, we have just a few diagnostic lines to measure radial velocity, and also we stick just to one line to measure actual radial velocity in order to see the peak-to-peak amplitude of radiation velocity. We just stick to the most prominent one, helium 5876, because if we will took all of them and measure for the same star radial velocity for all these lines, like for extreme fast rotators, like the spread of velocity was very huge, just because the line profiles are so wide and the rest of the lines are not really prominent. So we are diving in there, so that's why we kind of investigated this area. Kind of, yeah, to show the behavior. And then again, that TESS provide us kind of a nice opportunity to see what is photometric variability for all of this target, but we need to find the size of the the test pixel size relatively big. It's 21 seconds. That we need to keep in mind about contamination that we have nearby. So like this is a green area where we have a which we collect the light, and like it will be our final light curve based on this pixels, but we need to really be careful that maybe we got some other contamination for the other star if we are in a very crowded area. Kind of what we investigate as well, and we end up that we have kind of different nature of metric variability of all stars. Surely we have a really nice eclipsing binary, not many, but we detected, and that depends on the spectral type, either giant or dwarf sequence. We see the low or high frequencies in pulsation, which we will need to investigate more further, but let needs this job to the astroseismology, because among them for sure we will have some mergers, but we need to have a merger model to understand where is the merger here. What the kind of side projects that we will need to do. And then the final part is to see the runaway status of all. And we also complement our data with slower rotators. And we really can notice that the fraction of runaways in the fast rotating domain is much larger than the slow rotating domain. So we really see that if we define the stars at fully velocity more than 30 meters per second, so that's kind of tangential velocity of all of them, and we see that kind of we have dominance of runaways in the fast rotation domain, which we'll discuss later why it's happening like this. And here is a kind of final picture of where we try to describe all of our targets. So here I'm selecting the vsini versus peak-to-peak radial velocity for the target. So peak-to-peak is amplitude radial velocity in a given epoch. So we see that clearly we have some binaries as V1 system, which are, most of them are eclipsing binaries, which are like label them accordingly. And a huge fraction of likely single star, among which majority of them are runaways. And yeah, and we can see that even with peak to peak 50 kilometers per second, we define them as likely single because with such broad profile, I mean, we should not just put a simple threshold that among this very, if we are more than like certain radio velocity estimate, we should define them as a binary. So we need to go one by one spectrum and to see what is the real variation in the line favorability. And on top of it, we also compare it with, I mean, we did the same work for slow rotating domain, where we put also all type fast slow rotators. And this gray line is just sees the effect of inclination, because we don't know inclination in vast majority of them, especially if it's not a binary, we don't know as an orbital solution, so just effect of inclination.
Nikolay,
Yeah.
I'm not sure I understand what your Y scale is. Is this the systemic motion of the?
No, it's a radial. It's a variation in radial velocity, amplitude of radial velocity in a given. For example, we have a 20 spectrum. We measure all radial velocity of this 20 spectrum. So the maximum amplitude which reaches the star within this 20 spectrum.
So it's a measure of the binding energy or the semi-major axis or something. Right?
Semi-major axis. It's a half of semi-major axis.
Yeah. Okay.
Twice of semi-major axis.
Yeah. Right. But there's a mass term there as well.
Yeah.
Okay.
So it's just which we get amplitude of the radial velocity. Which we get. Speaking about. Oh, okay. Now we enter the most funny, interesting part. Same amplitude. That's what we asked it. It's we can transform it to the peak. And we know that there are some works which predict some OB plus black hole system, and we actually know because it was very well known binary, which was the.
Can you tell us what the legend says, since we don't see it? So what are the colors? Red is.
Oh, it depends. The mass transfer case A, case B. So we expect. So it's kind of a simulation of all B plus black hole binaries, and depending on the where mass transfer were occurred on the main sequence or after the sequence.
Which is A, which is
what?
can you see
Case A on the main sequence, case B after the sequence. Case B.
Maybe we can minimize it.
Yeah, I don't know.
if you can.
But I can.
But I mean, he's projecting, not me.
Yeah, you can. Go on the minus up there.
Ah,
Yeah.
perfect.
Great.
So, and that's one thing which kind of really give us, attraction that in this among all the systems we could have kind of interesting binary configuration, because indeed, if all of them are post-interacting objects, what is the second companion? Because according to simulation, it can be very exotic objects from like SDO, strip star, black hole. That's another story how to detect them. And with this picture, I start to like investigate and like to go in more details in order to characterize all this system, because we know even the periods for some of them, and depending on the period, we can kind of already have a preliminary conclusions from where, they can get such fast rotation, especially if we have such a high fraction of runaways, because we have just two channels that can give us a runaway star. It's all disrupted binary after supernova explosion, or with like dynamical ejection from the crowded region. What is more dominant? I can already say that
The percentage is from all the stars or from just
from some stars. That's from all my sample of 54 fast rotators.
so this percentage of fast rotators? Not
Yes,
okay.
yes, it's a percentage of fast rotators.
What is alternatively?
Line profile variable means slightly single, means apparently single. So line profile variable due to non-binary. So it's kind of we.
Our non-detected component.
Yeah. So there is some small variation, but we can, even from visual inspection, we can't say that it's really a binary. So we assume it is likely single star. Okay, so this is kind of what we need to do for sure, because really among this target, kind of would be a really nice system which can actually tell us about the origin and fast rotation as well. Okay, now let's play a bit. And someone told me what it is and why we have such light curve. It's a TESS light curve for some of our tasks. No, actually, what we see here, okay, the question is like this. Nice.
And reflection effect.
Oh, good reflection effect. Because of what?
Heating from the companion.
Heating
Well,
from the companion.
yeah, one side of the
Oh,
star is
okay,
gets
yeah,
heated by the
got
high
some
energy
hints,
emission
okay.
from the compact companion.
Perfect. It's not yet the answer. Okay. I superposed, but you almost got it. So I superpose the same light curve with a velocity curve. So yeah, the presence of eclipses and light are happening perfectly. But the reflection effect. I modeled the system actually with, but there is one small difference in these two. Can you spot the difference? And it's regarding the reflection effect.
Is on under the
Very good. And what does it mean? Why it can happen? Yeah, that's actually a very important thing. That because at the beginning we also thought, yeah, reflection effect. So we have some really hot companion, extremely hot companion, yeah, which reflect to the primary. And yeah, but what's the difference here? And the velocity will be always the same because, of course, the primary.
Well, I mean, I would say the right-hand side, you have more brightness because you see the heated side of the companion, but and then you have a little dip because.
But it's not much important. The most important, as you spotted, is actually how we start the phase. So why we have at the beginning here and small at least, and right. Okay, I will. Okay, I will give you the beer in any case, but but the answer is here. That we really need to know, we need to be aware who is much hotter here, because if we assume initially, okay, we have very hot companion here, and we see a reflection of this secondary of the primary. Okay, we can be very happy. Okay, this is SDO, and let's be very happy about our findings. But if we don't know the radial velocity curve, we can very easily to make a mistake to see what is actually reflecting, which reflection we see, and only with a radial velocity curve we can answer it, because radial velocity curve will give us a actual the phase, because very easy to start the phase here, and then we will mix up. We will have just light curve. So we need always do this analysis with a radial velocity curve. And then we can see that at each conjunction we have each eclipse. And it's kind of very important.
Okay, so you're saying that you get the same curve at the bottom, independent on temperature or the temperature of the companion. So you have a companion that has 10 Newtons and the other one is 75,000, and then the curve at the bottom look the same.
No, yes, they will be the same.
Is it the same?
Yeah, they'll be the same. Radials would always.
Yeah, rather those look the same. Then you have
And
to-
that's very, very important, I mean, to keep in mind, because that actually will help I mean, us to understand with nature of the system which we are dealing with. Okay, and when we find out what is going on, okay, why we have this O-type fast rotator and kind of normal star nearby, so why isn't this star is rotating fast? Because in this case, it will be very easy. So it's a post-interacting object. Here we like mass transfer already occurred. Here we have a street star or something as a result. So here I have no question about the nature of this, but then I will have then this configuration, why this rotates very fast. And here, like the most fun thing is going on. Like I start to, because I found 3 such objects, and then I started, I'm sorry for the quality of the plot, because it's just what I having output of my modeling, because now I just start to model all the systems in detail, because I have initial conditions, and then I need just to reach. So like evolution of rotational velocity with H, and here like dashed lines is the rotation which I have now, we're observing now. So from the initial point, I need to reach up to what we see. This what kind of will give us the physics what's going on. But this work in process, because also investigating what is orbital angular momentum, because we need to see the tides, because maybe tides will give us also something, but I'm not sure if the tides will give such rotation. That's kind of also explored. Yeah.
I'm saying just with one solar mass companion, you are able to spin the thing up.
No.
No.
This speeding up, yeah, very nice question, because it's a 10 million years, and this speeding up just because the primary already in the end of the main sequence. So the radius of the star is very big already, so it's speeding up not because of the tides, it's just because the size of the primary. That's why also we need to see because we need to be aware of H. Yeah. And
sorry, I didn't understand it.
Yeah.
If you expand, you slow down, right? I mean, why do you get a faster rotation if the star gets larger?
Just transfer of
The tidal
momentum.
the tidal synchronization.
It's not directly the tidal character. Nice question, but I mean, I don't want to make a mistake here. But
It's due to the companion. It's not an internal.
no, it should not be internal. There is some internal one, for sure. Really, I don't want to now because I'm still investigating it. But
Okay, so the 8, this is tens of millions of years, right?
yeah, and with such, I mean, yeah,
So the
like 50.
10 to the 7.
Yeah.
Okay.
And then also we need to see, so here is the same simulations, but I am varying the initial rotation, because maybe initial rotation can give us a hint. Okay, it's just for one star, but different range of initial rotation. And this dash line is like what we see for a given star. So in this case, maybe initial rotation can give us. But in this star, I can't really, it's most like one of the faster, really rotates very fast, and I can't even reach this fast rotation with, again, if I initially will make this.
So, excuse me, a very naive question. I understand that this is a model and we did this equation very recently, but what is the physical mechanism that you are representing in this model, that this model is reproducing? So why you have this initial rotation velocity for the mass star with a low mass companion, and then it goes one way or the other, depending on the initial condition. But what is behind, what is the physical mechanism behind that?
Okay, this they're going out because of mass loss. So it's we lose the angular momentum because star mass low and they're quite massive. So that's the main reason why they're slowing down. This is and at the end it's just because star is expanding. We have small hydrogen core.
But it's not caused by mass transfer from the companion. So if you increase the mass of the companion, would you?
Here is one, just one. Look the.
Yeah, no, but what I'm saying, like
yeah.
you put one, but if you
Yeah.
put 10, like would you, gain more angular momentum because you're like transferring more mass? Or?
I just did it 3 days ago. I will answer to this, but it's really kind of we need to enter the physics what's going on. But yeah,
But in the model, I'm asking about in
Yeah.
the model, what are you modeling? What are you putting inside the model?
I'm modeling
which kind of physics is behind, or you have too many ingredients and then these spikes at the end are very difficult to interpret.
there are, since I'm looking at math, it's really a lot of physics, but it's physics mainly which are kind of agreed for, the parameters which agreed to be suitable for massive stars, like, in terms of mass loss and, and other things. But also I put it like with tidal synchronization, with mass transfer. So
there are many pieces, so
Yes.
it's good to know
Yes.
what is the main factor behind the last spike.
that's kind of my main thing what I want to answer.
But
as
it's mostly case A mass transfer, right? So
Sure.
it's mass transfer during the main sequence.
Sure, but we even don't go beyond the sequence yet. No, it's kind of will be a next thing. Now, like in this exercise, I want to see first tides and then what's the effect of initial rotation, because then I even didn't enter yet the mass transfer. What will be after the mass transfer? Because I'm now in modeling it with pre-interacting mode. The post-interacting, I will do later. But first we need to see, because we know more or less the age, and for example, for this star, it's not more than 1 million, because it's from the cluster. And more or less, maybe it's also rejuvenated, maybe it was a merger. But for this particular star, we know that it should be, it's a real age.
So then there's
And
no
how
way
the-
to get
And how? That's a nice question, how to get it.
And then you need to put a secondary that's much more massive and maybe closer.
It's running now. It's what yes.
Are all your sources in clusters?
Not all of them. They're mainly from field, but some of them in the clusters. Some of them. So because age and strain be extremely needed, because we really need to know where we stop it, but maybe 10% of the stars in the cluster. Okay, so how many minutes we have? Just now.
37.
Okay, let just to see user application. So here, so I put all the fast-rotators together with slow-rotators, the gray small dots on the spectroscopic H-R diagram. And what we really can spot, and what is really interesting, which kind of connected the evolutionary path, why we have all SB1 system binaries are located in the low, low part of the diagram, but we don't have binaries here at all. We can just runaways, like it's runaways. I don't know the real answer, but I can just speculate a bit why. I mean, mainly because of the simply they're more massive and they evolve faster, so we don't see already the second companion because it's evolved very faster and always black holes there or something very phase that we don't detect. Because if we compare it with a slow rotating domain, so now it's kind of it's just a slow rotator, but with the same kind of labeling. can see that in the rotating we have binaries even in this part as well. And yeah, we already did some work where we investigate what is the rotational distribution in the different parts of the H-R diagram. And I mean, what is the rotational distribution of binaries? And we can see that most of the fast-rotators, which are binaries, are located in the lower part of the diagram. So it's again give us some clues about different evolutionary paths. Okay, so just to finish up, like the main conclusion is that we compare the statistics of binaries in different domain. We see that we have much larger percentage of two component spectroscopic binaries in the slow rotating rather than fast rotating. Means like we can already speculate that because here is a pre-interacting system, here is a post-interacting system. But again, we need to confirm it with real simulations. And yeah, the percentage of runaway, we have extremely high percentage of runaway.
What is SB1 as we choose for
Sorry, I didn't define it. One component spectroscopic binaries. We see it's a binary, but we don't see the. Here we see the clear two. In the spectrum, we have the two lines, and meanwhile here just one line, which is moving, but for sure there is something which forces the stuff,
which might be a star or a compact object.
Exactly. So that's why we are kind of very interesting to look immediately to SB1 system, because the most of the thing will be in SB1 system, because we need to reveal the nature of this system. Yeah, and here is the overall distribution. Just nice representation of population of all binaries that we have. Very nice to see the amount of runways in the likely single domain. Like majority of them are going from disrupted binaries after a supernova event. And I will not even enter the BPAS modeling. Not have time. Just to sum up and to emphasize what maybe next one. Just we really need to first of all to systematize all the binaries that we have from O to B and maybe A, and go maybe even to the supergiant domain in terms of binary fraction, because we know that binary fraction is decreasing from O to A. From O to ABA, supergiant. And that kind of empirically will help us to constrain the further theoretical simulation, because then I want to reproduce the observer properties of all these fast rotators, and then we can actually follow the actual paths, from the beginning, from star formation to the even maybe a supergiant, my ideal goal. So yeah, thank you very much. Actually, that's
questions. So did I understand the talk properly? So I got from your talk that basically these fast rotators, they tend to be objects which might have evolved enough in a binary system in order to interact somehow and get this extra angular momentum. Yeah. Or you have these strange cases where the companion is a low mass star, and in that case it's more mysterious what is going on. Exactly. So initially we thought that, because we were biased maybe even by theoretical predictions at the beginning, that they should be most of them post interacting binaries after post mass transfer or mergers, and very small initial rotation.
But if the companion is a low mass star, it would be the
exactly
second, it would be the second companion, not the first.
Yeah,
maybe companion.
The example which I showed you, when we really, that's for sure not the SDO, it's not some exotic, it's really very young star with a companion normal temperature. So why it gets such high angular momentum. So that's kind of a question. Which we want
But it is possible that it's the second companion, that it has another companion with a higher temperature beforehand? Like, how do you know it's the first companion of the star?
You mean a triple system? Or?
No, that it changed companions at a certain point. In global clusters, for example, it happens. You can be the companion of
Exchange.
one star, in this case, then it exchange companion. With neutron stars, we have this debate whether it changed companion. And how do you know that it changed companion?
And that's why I asked whether they were all clusters, but it's a very small fraction. But the ones that are runaways, they could have been in clusters, right? So
Right.
you could have a dynamical exchange that kicks out the binary and leaves with another companion than it has originally, and then all your BPAS guesses are off, right? Because you allow for 2 stars initially, which there were 10,000 initially, then
Right.
you can round space is wide open, you can do whatever you want. It's a bit lame, but you can explain it with binaries to move to cluster dynamics and triples, but
It could be seen as a proof that it changed companions somehow, and the question is how, right?
but you can trace back these runaways, right? And you can see
Yeah, of course we
whether it makes any sense. If they're too far away.
Yeah, we can trace back and to see where it came from, other clusters around.
Yeah,
Yeah, that's kind of a nice check, you know.
Because I was sorry, there are a lot of fast-rotators, B-type stars, B2, near to the breaking of the rotation for the centrifugal force, 500 kilometers per second. Some of them are not binary, so or you have not demonstrated that they are binary. So they
Yeah,
are
majority of them are single, yeah.
exactly. That's true, no? Okay.
No, that's true. I mean, first
my,
of all,
my
we did,
question, which is the percentage of binaries in B2 type stars with
no, if
vsini
in all
large-
type star we have a 70%. In the B type, it depends how you define the binaries. That was also a question because
No, I know this is a question.
yeah.
But there are a lot of single stars that are rotating very fast that are not in binary systems. So
True. And also it's a question of B or BN stars. It's another thing.
and they are in clusters because they are evolved and you can see how they are defined. They are defined in the entire diagram. So we're placed above the isotope that they are assigned. Okay.
So yeah, again, but why they rotate fast? I mean,
No, it's the same question. I don't know the
That's
origin
kind
of
of-
information. Yeah.
but,
Oh, yeah, because I mean, yeah, some works have shown that, I mean, in principle, you think like, okay, they're merger products and that's why they rotate fast. But then like, yeah,
But
like
it's
recent
not-
work showed that, you create a high
It's
magnetic
not,
field, there's magnetic braking,
yeah,
so you
so
actually slow down.
yeah, magnetic braking thing. Then we don't expect mergers to rotate fast.
Yeah, I mean, yeah, very recent mergers, yes, right? But it goes very quickly into a
Exactly.
slow rotating regime, so.
And that how to distinguish merger from not merger is like this thing. Here, maybe the astrosysmology will help us. There's
But-
only one thing that we
Yeah,
can-
before you mentioned that you need a merger model, but like,
Yeah.
why merger should pulsate? I mean, like,
where I expect naturally some hints in the photometric variation of some merger, recent merger event or something.
right, but yeah. I mean, the star will be perturbed, but eventually it will settle into like equilibrium, right? So I don't know.
You're right, yeah, but just a hint. And another thing I forgot to mention is the abundances. Also can be another thing, but here I plotted like nitrogen and hydrogen, nitrogen and helium, all the fast-rotators with some, extra model, but we don't see really a pattern so far. Just a completely natural evolutionary enrichment of helium. But also it can give us something because if it's merger, it can be helium enriched and nitrogen enriched. Also depend on the model, but we also, I mean, looking forward towards this direction, but from the really preliminary analysis, we wouldn't separate them at all.
Yeah, maybe another
Thank you.
question, yeah. For your candidates, did you also check for like X-ray surveys
Yes,
or
we
like
checked
high energy, like Galax or kind of?
We XMM, there are some of them. They're all X required. We didn't. I mean, from the sample of 50, we have just 10